interaction of radiation with matter continues, and the interaction of heavy charged particles. We have discussed some terms. The first 6 terms have already been discussed. So in this class, we will be discussing these terms: energy loss in absorbers, scaling loss, behavior of fission fragments, and secondary electrons. So the first one, energy loss in thin absorbers. For thin absorbers, that means or detectors that are penetrated by a given charged particle, the energy deposited within the absorber can be calculated as. That means when a particle is passing through a thin absorber, it is not stopped there. It is entering that absorber with a particular energy, and it is piercing that absorber and coming out with an energy which is less than the initial energy, so that some energy is lost within the absorber. So what quantity of energy is absorbed in the absorber, or what it is deposited by the charged particle in the absorber, can be calculated using this equation as delta E equal to minus of delta E by dx, this term known to us as the specific energy loss average into T. That means you will find out what is the average specific energy loss through the material. That means it is the energy deposited in unit distance. So if T is the thickness, if you multiply with that thickness, you will be getting the total energy deposited. In this equation, we will explain as where T is the absorber thickness and minus dE by dx average is the linear stopping power averaged over the energy of the particle while in the absorber. If the energy loss is small, the stopping power does not change much, and it can be approximated by its value at the incident particle energy. That means if the loss is small, in place of this dE by dx average, you can consider the value. What is the initial loss? If you know that value, you can directly use that value and you can multiply it with the thickness to get the energy loss. And these are the range corresponding to different energies can be calculated, and the range energy curves can be plotted for different materials. And here we are using alpha particle. This is the alpha particle energy, and it is increasing. You can see that there is also increase in range, and we have used different materials like this one. You can see as it is helium, and this is silicon, this is germanium, and this is gold, and of course you have hydrogen here, and above this helium you can see that green graph. They are almost close, this hydrogen and this helium. And what is the use of such a graph? That means these were range energy curves that we can discuss next. These types of curves can be used as a reference standard. What is a reference standard? Range energy relations are extremely useful in particle energy measurements. We have already mentioned that for a particular particle with a particular energy and in a particular absorber, the range is fixed, that we have already mentioned. For absorber thickness through which the energy loss is not small, a properly weighted minus dE by dx average can be calculated with the use of range energy plot. And this is the reason, one of the reasons that you are using this. You can find minus dE by dx average. And the method is like this. The basis of the method is as follows. Let R1 represent the full range of the incident particle with the energy E0 in the absorber material. That means it is the range with the energy E0. By subtracting the physical thickness of the absorber T from R1. And here this is range and this is energy. So corresponding to energy E0, this is the range. You can calculate like this. From this E0, this is R1. And by subtracting the physical thickness of the absorber T from R1, that means this is the range. If say 1 centimeter is the thickness or half centimeter, from this R1 you can subtract that value T and you will be getting R2. And the energy corresponding to R2 can be calculated. That means a value of R2 is obtained, represents the range of those particles that emerge from the opposite surface of the observer. By finding the energy corresponding to R2, from R2, this is the corresponding energy. The energy of the transmitted particles ET can be calculated. So the deposit energy is E0 minus ET. So this is the way by which you are calculating the energy deposited. We have already mentioned in the last class that by having an idea regarding energy and range, you can calculate the amount of energy deposited. Or if you know the initial energy, that means if this is the energy, you can directly calculate what is the range. And if say this point is the initial energy, you can calculate what is the range. So by knowing energy, you can find the range. And if you have a thin absorber, if you know the initial energy, you can calculate what will be the energy of the emitted particle or what is coming out of the absorber by knowing the thickness, and by subtracting those two energies you can find the energy deposited. And now some scaling laws. Scaling means actually you are formulating it based on some known facts. Sometimes data are not available on the range or energy loss characteristics of precisely the same particle absorber combination needed in a given experiment. Based on Bethe formula and on the assumption that the stopping power per atom of compounds or mixtures is additive, the Bragg-Kleeman rule is given as. This is the rule. For example, if you have a particular compound made up of compounds say A, B, C, D, etc. And you know what is the range in A or B, C, D, etc. But when you are combining them for some experiments, you are making some compounds. But the property of that compound is not yet studied. So what you have to do is, you can use the data of A, B, C and D, and you can find what will be the value when they are that A, B, C and D are using as a compound. And the equation is 1 by Nc equals d by dx of C is sigma over I Wi 1 by Ni d by dx of I, where the terms are, where this N is the atomic density. This N d by dx is the linear stopping power. Wi, this one, represents the atom fraction of the ith component in the compound, subscript C. So this C stands for the compound. So 1 by Nc is the atomic density of the compound. and this d by dx of C is the linear stopping power of the compound. Actually, we have to calculate this one. And this Wi means it is the atom fraction of the ith component in the compound. For example, if you are considering, say, water, H2O, so that H has 2 fractions and O 1 fraction. So similarly, in a compound, there will be 1 by third factor, other will be 1 by third factor, then 2 by third factor, etc. In that way, you can calculate what will be this Wi, that fraction. And 1 by Ni represents the atomic density of that ith factor. Then Ni, and d by dx of I is the linear stopping power of that particular component. So by knowing this, you can calculate this one. As an example of the application of this equation, the linear stopping power of alpha particles in a metallic oxide could be obtained from separate data on the stopping power in both the pure metal and in oxygen. This is normally applied in several cases. So actually, you are familiar with the individual components, and using that you are finding, that means you are scaling it to find out the combination as a compound. And if you are actually varying the percentage in the compound, this will be different. So it can also be calculated. So there is no need to do further experiment for that. You can directly calculate it. This is the advantage of such scaling laws. The range of a charged particle in a compound material can also be estimated, provided its range is known in all the constituent elements. Just we have mentioned about the specific energy laws. Similarly, the range can also be calculated. In this derivation, it is necessary to assume that the shape of the d by dx curve is independent of the stopping medium. That means it is a straight line or it is a curved one, and that shape is retained irrespective of the medium. In the last range energy curve, we have shown that all are curves, and if one is straight line, other is a perpendicular line, such thing is not applicable. That is why this concept, the shape of the d by dx curve is independent of the stopping medium. Under these conditions, the range in the compound is given by Rc equal to mc by root divided by sigma over I Ni Ai Ri. Here also, Ri is the range in the element I, Ni is the number of atoms of element I in the molecule, Ai is the atomic weight of the element I, and mc is the molecular weight of the compound. And this I is the element. And another semi-empirical formula, you know that term semi-empirical, which has no experimental derivation, etc., or you can't derive it in some ways, but it is based on some experiments. You are actually formulating it, and there is no actual derivation for that. If range data are not available for all the constituent elements, estimates can be made based on a semi-empirical formula called the Bragg-Kleeman rule as R1 by R0 approximately equal to ρ0 root of A1 by ρ1 root of A0, where this 0 and 1 represents two elements, where ρ and A represent density and atomic weight. The subscript 0 and 1 refer to different absorbing materials. The accuracy of this estimate diminishes when the two materials are of widely different atomic weights. So it is always best to use range data from a material that is as close as possible in A to the absorber of interest. That means, suppose you want to know the range of a material whose, say, atomic weight is 56. And if you know the property of 54 or 55, you can consider this A0 for that one, its density, its range. And for this 56 or 55 value, you can calculate, 56 value, you must know what is the value of A1 and ρ1, then you can calculate the value of R1. But for that 56 one, if you are using a non-compound with the value, say 100 or some 20, that will not be accurate. So this A1 and A0 must be almost in the range. Then this will be a fairly good one. If the range data are not available for all the constant elements that we have mentioned, so it is always best to use range data from a material that is as close as possible in A to the absorber of interest. Range data can also be generated to different charged particles within a given absorber material by integration of Bethe formula. Actually, in this topic we are doing that. We have some data, and that data can be used to create new, that data of some non-elements can be used to find out data of some unknown materials. That is why you are calling it as a scaling laws. So you have your famous Bethe formula. It can be shown that the range of a particle of mass m and charge z can be represented by. So we are finding out the range. Just we have mentioned that the range can be found out using an empirical formula for almost similar atomic weights. And this is from Bethe formula. This is your Bethe formula. Minus d by dx is 4 pi e raised to 4 z square m0 v square nv, where this z is the atomic number of the particle. This n and v corresponds to the material, absorbing material. m0 v is the velocity, all are known. Where this is the electronic mass, where Fv represents a unique fraction of the particle initial velocity v. This is Fv represents, or it denotes a function which depends on the initial velocity. Then range for a particular velocity will be m by z square, a function of v. For particles of the same initial velocity, this factor will be identical, and therefore we can write as R of AV equal to MA by ZA square of FV, similarly RB. So that RA by RB, RA of V and RB of V will be MA ZB square, MB ZA square. From that you can find the value of RA as RA of V is equal to MA ZB square by MB ZA square RB of V, where the subscript A and B refer to different charged particles. Thus, the range of a particle, say A, for which data are not available can be estimated by calculating its initial velocity, finding the range of any other particle, say B, of the same initial velocity in the same material. That means, if you have alpha particle, you know the properties of alpha particle. Suppose you want to find out the property of proton for the same initial velocity, you can use the data of alpha particle to find that of proton, provided they are moving with the same initial velocity, not energy, initial velocity. These estimates are only approximate because no account is taken of the change in charge state of the particle as it nears the end of its path. We have mentioned that when they are coming to the end, they are absorbing electrons. Correction factors need to be applied to compensate for this effect and predict the range more accurately. And this has been done by so many people, and actually now we are not at all interested in going further, and for us this is sufficient. So this about scaling laws. So in scaling laws we have mentioned that we have some non-data, and that non-data can be applied to find out the properties of some unknown ones. That is why it is known as scaling laws. And next is behavior of fission fragments. This fission fragments means they are heavy ions. And so far we have mentioned only about protons, neutrons, alpha particles, etc. They are lighter ones. The heavy fragments produced as a result of neutron-induced or spontaneous fission of heavy nuclei are energetic charged particles with properties somewhat different from those of lighter particles like proton, alpha particles, etc. We can see the differences. Because the fragments start out stripped of many electrons, their very large effective charge results in a specific energy loss greater than that encountered with any other radiations. This you can understand with the concept of your Bethe formula. There you have, in numerator you have small z square. Here that z is the charge of the radiation, that is very high. So your specific energy loss will be much larger. The initial energy is also very high. However, the range of a typical fission fragment is approximately half that of a 5 megaelectron-volt particle. This is because the specific energy loss is very large, so range will be small. An important feature of a fission fragment track is that the specific energy loss decreases as the particle loses energy in absorber. This behavior is in marked contrast to the lighter particles such as alpha particles or protons, and is a result of the continuous decrease of the effective charge carried by the fragment as its velocity is reduced. This is your Bethe formula. The pickup of electrons begins immediately at the start of the track, and therefore the factor z in the numerator of Bethe formula continuously drops. We have mentioned that for normal particles, they are picking charges only at the end of their range. That means just before they coming to stop. The resulting decrease in dE by dx is large enough to overcome the increase that normally accomplishes a reduction in velocity. That means when this velocity decreases, you can see that this ratio actually increases. When velocity decreases, this ratio increases. But the decrease in z is very large. That means this is increases, but this is decreases at a rapid rate. Therefore, this minus dE by dx actually decreases. For particles with much lower initial charge state, such as alpha particle, electron pickup does not become significant until the near end of the range. There, actually, your velocity is decreasing. So, there will be an increase in this quantity that is known to us. But here, this Z, that means there are a large, it is a heavy ion with the very large positive charge. So, it can easily attract electrons. So, at the starting stage itself, electrons are coming to this. That means its charge is continuously decreasing. That is why you are getting this dE by dx as decreased as the particle is entering into the medium. But for this is for heavier ions, and for lighter ions, that picking up of charged particles is only at the end. That means for both cases, actually velocity is decreased as they are going in. So if the z is unchanged, you can see that this dE by dx increases. But for heavy ions, this z also decreases. That is why this quantity decreases, and for other quantities it increases. And the last term, secondary electron emission from surfaces. As charged particle lose their kinetic energy during the slowing down process, many electrons from the absorber are given a sufficient impulse to travel a short distance from the original track of the particle. These include the delta rays that we have mentioned earlier, whose energy is high enough to ionize other absorber atoms. Electrons whose kinetic energy of only a few electron volt is below the minimum energy for further ionization. So, when the charged particles are moving, they are actually pulling out electrons. That means they are getting sufficient impulse to travel a short distance from the original track of the particle. So, some electrons are coming out with velocity, and they are you are calling as the delta rays. If an energetic charged particle is incident on or emerges from a solid surface, some of these electrons may migrate to the surface and have sufficient energy to escape. The term secondary electrons is conveniently applied to these escaping low energy electrons. So our delta rays are somewhat secondary electrons. But if the electrons coming from are just exciting to a higher energy stage, that means they are not ionizing, they cannot come out of the atom. A single heavy ion such as fission fragment can produce hundreds of these escaping secondaries, whereas lighter alpha particles might typically result in 10 or fewer secondaries per particle. Because their alpha particle energy is low, so the energy that is transferring to electrons are already also low. That is why a limited number of electrons. But in case of fission fragments, energy is very high, so a large number of secondary electrons can be emitted. And that about the properties of heavy charged particles. And in next session, we have already mentioned about the fast moving electrons in unit 1, and here we will study the properties of fast moving electrons that we can do in the next class. Thank you.